Swayam Prabha. Digital India. Educated India.
So, welcome to today class of nonlinear vibration. So, this is the second class of second module. So, in the last class we have started with the derivation of nonlinear equation of motion. So, where we have discussed regarding the lumped parameter model and or the distributed mass model. So, two approaches just I have introduced, and I have told you regarding the force and moment based approach, where we have used this Newton's second law and D'Alembert principle to only the lumped parameter models. So, today class we will see this application of this force and moment based approach, that is the Newton's second law or D'Alembert principle, to this distributed mass system or continuous system. So, distributed mass is otherwise also known as continuous system. So, today class first half will study regarding the force and moment based approach, that is application of Newton's second law and D'Alembert principle to continuous system. Two examples we will see how to derive this equation of motion, nonlinear equation of motion, how they are different from these lumped parameter models, and then we will go for this energy based approach, where briefly I will tell the application of this Lagrange principle and extended Hamilton principle to derive the equation of motion. So, last class we have started with the derivation of equation motion of a simple spring mass system. So, initially taking the spring mass system as linear. So, we have derived this equation of motion as mx double dot plus cx dot plus kx equal to f sin omega t. So, here you have to draw the free body diagram and write down the equation of motion by using this Newton's second law or the D'Alembert principle. So, later the spring and damper can be converted to nonlinear spring or damper by considering a soft spring or hard spring. So, then this equation of motion of the spring mass systems can be written using the nonlinear equation of motion. We have taken a second example of this pendulum, simple pendulum, and in the simple pendulum already by writing the forces and this acceleration. So, we can write in vector form, we can write down the equation of motion. So, the equation of motion, governing equation of motions we got in this form, that is theta double dot plus g by L sin theta equal to theta. When this theta is small, so then we can consider the sin theta equal to 0, and the governing equation reduces to theta double dot plus g by L theta equal to 0. But if theta is not small, then we can expand the sin theta equal to theta minus theta cube by factorial 3 plus theta fifth by factorial 5 minus this theta to the power 7 by factorial 7, and we can write down the nonlinear equation of motion in this form. So, where this equation reduces to theta double dot plus g by L into theta minus theta cube by 6 plus theta fifth by 120 minus theta to the power 7 by 5040. You just see the coefficient of theta 5 and theta 7 are very small. So, theta 5 coefficient is 1 by 120 and theta 7 coefficient equal to 1 by 5040. So, these two terms can be neglected and one conveniently can keep the equation up to third order. So, the equation will reduce to theta double dot plus g by L into theta minus theta q by 6. So, which is similar to that of a doping equations, what we have studied or what we have seen in the introductory class. So, also I told how by using this moment also you can find the equation of motion for the same system. Then we have considered the 2 degrees of freedom system. So, the primary system in the primary system we have added the observer. So, another spring and mass system and derive this equation motion for the tuned vibration observer. So, it can be made nonlinear by using this nonlinear springs also. So, we have seen the example of a active vibration observer, whereby we have put this piezoelectric stack actuator. So, this element is the piezoelectric stack actuator. By putting that piezoelectric stack actuator, so and drawing the free body diagram, so one can write the equation of motion of the system. So, this shows the equation of motion of the system. So, this Fc is the actuator force, so which can be written in this form. So, this way by using the free body diagram, so one can find the equation of motion for 1 degree of freedom system, 2 degree of freedom system or multi degree of freedom system, or one can find the equation of motion for lumped parameter system. So, today class actually we are going to study the equation of motion for the system with continuous system. So, we will study the equation of motion for continuous system. So, let us start with the continuous system, for example, this Euler-Bernoulli beam. So, in case of Euler-Bernoulli beam, so this is a beam, Euler-Bernoulli beam is a beam, slender beam subjected to bending, pure bending. So, this is subjected to pure bending. So, it can be, so in this case the beam can be supported in many different ways. For example, it can be a cantilever beam. So, if the one end is fixed, so it can be a simply supported beam also, or fixed beam. Let us first draw the fixed beam. So, if both the sides we are fixing, then this is a fixed beam. We can have a simply supported beam. So, if one end is, so let us put one end roller supported and other end hinged. So, if we are not putting a hinge here and both end roller support, so in that case by applying an inclined load, so the beam can slide over the roller. So, that is why one end must be hinged and other end must be roller supported. So, this is simply supported. So, this case is simply supported beam. So, this is fixed or okay. So, this is fixed and this case is cantilever. So, unlike the lumped parameter model, so where the equation motions are written by using the simple differential equations. So, here you can see the equations can be written by using partial differential equation, because the displacement of any point. So, let us take this point, the displacement of this point is a function of both space and time. So, it is a function of both space and time. So, we require a partial differential equation to write down the equation of motion. So, let us first derive the equation motion of a simple Euler-Bernoulli beam, and then we will see how we can make this equation that of a nonlinear equation. So, initially let us find the equation of motion of the Euler-Bernoulli beam. So, let us take a small element, for example, you take any of the beam and just take a small element, let it is subjected to a loading condition, that is f x t. Let a force f x t or g x t, let us write g x t, already we have written f for something. So, let this is the force acting, we keep with f x t, no problem. So, let this is the force acting here, it may be uniformly distributed loading or it may be any other loading acting on the system. Then, so it will be subjected to, as it is subjected to pure bending. So, we can write m. So, this side it will be m plus del m by del x into dx, and also the shear force. So, let the shear force this side equal to F. So, this side it will be in this direction. So, it will be equal to F plus del F by del x into dx. So, this is the force acting on the right side of this thing. So, let us assume that there is small variation of the force along the length of the beam, and also, so we are taking a very small element. So, this elemental length, let the elemental length is x, which is at a distance x from any of the end, or let us take from the fixed end of this thing if we are taking a cantilever beam. So, now by doing this force balance, so let us do the force balance. So, by doing the force balance, we can write the equation of motion. So, we have to do both force balance and moment balance to find the equation of motion of the system. So, it is derived this way. So, you can see. So, okay. So, let me write this equation, or you can write F or you can write V also. In some books this F is replaced by V. So, the equation of motion will be F. So, F is upward, let us take upward force positive and downward force negative. So, net force acting on the system will be equal to F, then minus F minus del F by del x, del F by del x into dx. So, here F is the shear force we are taking, capital F is the shear force we have taken, and plus the load acting here. So, the load acting here we are writing. So, the load, let us assume that the load acting, so instead of taking the sign, so let us assume that load is Fxt. So, it can be plus or minus, so no problem. So, if we are assuming this Fxt force, let the Fxt force direction is upward, small Fxt. So, that is why we have taken this plus, we are taking this upward force equal to positive. Then, so this net force must be equal to, so this net force will be equal to rho, that is the mass, this is mass per unit length, rho, and dx. So, this is the mass. So, mass of the element into, let W is the vibration, the displacement in this direction, transverse direction, then it will be del square W by del t square, that is the acceleration. So, by applying this Newton's second law, so this is the net force acting on the element. So, it is equal to F. So, this portion you can write that this way also, F plus del F by del x into dx plus Fxt. So, this is the external force acting, this part is the external force acting. So, this is the external force acting on the system. So, this F is the shear force. So, this part is the shear force. So, this is the shear force in the left end. So, this is the shear force in the right end, and this is the external force. So, this is the mass of that element, mass of that element equal to, so we can have the mass of the element rho dx, rho is the mass per unit length. So, this is the mass per unit length. So, we got this, and W is the transverse deflection, transverse deflection. So, transverse deflection in this direction. So, we can write the equation motion in this form. So, this is the mass into acceleration. So, now by opening this thing, this F and this F will cancel, then we can write this equation motion in this form, that is minus del F by del x. So, minus del F by del x into dx plus this external force F x t equal to rho del square W by del t square into dx. So, in the absence of this external force, in the absence of the external force, so you can write rho, or in presence of this thing also you can write rho del square W by del t square plus del F by del x del f by del x into dx. You can take this force also, so equal to f x t. Similarly, you can take the moment also. So, taking the moment, so let us take the moment about this. So, let us take about this axis. So, let this is your y axis, this is the x axis, this thing you have taken along x, this is along y. So, you can write the moment equation. So, moment equation will be equal to, so let your moment equation will be equal to, so if you are taking m, so m minus m plus del m by del x into dx. So, we are taking the moment. So, you just see, so we have this thing. So, this is the loading we have taken f x, f small f x t. So, this is shear force. So, this is shear force. So, this is f, capital F we have taken. So, this is f plus delta f by del x into dx. So, we have taken this is m and this is m plus del m by del x into dx. So, now taking moment about this line. So, it will be our y axis. So, m minus m plus del m by del x into dx, that is the moment. So, this moment you have taken positive. So, clockwise moment you have taken positive. So, anti-clockwise moment is negative. So, due to this force F, so F is passing through that point. So, this is equal to 0, then clockwise moment equal to, as it is positive you are taking. So, then it will be F plus del f by dx into dx. So, multiplied by as this distance equal to dx. So, this distance equal to dx. So, this is the thing. So, then we are taking this f x direction in upward direction. So, it can be written f x t. So, this let us assume that this total force is f x t into, so it will act in a distance dx by 2. So, this way we can write now this m and this m will cancel. So, the equation can be written in this form. So, that is minus del m by del x minus del m by del x plus, so you can write this equation f dx plus del f by del x into dx whole square. So, this part del m by del x into dx. So, this f x t into dx by 2. So, this way you can write, so this moment equation and force equation. Now, you can simplify these equations, and by simplifying these equations, so you can get these Euler-Bernoulli beam equation. So, which is nothing but your del E I. So, you can substitute m equal to, you can substitute m equal to E I del square w by del x square. So, because you know in pure bending m by I equal to sigma by y equal to E by r. So, this 1 by r is nothing but, so for a linear system, so this 1 by r for linear curvature. So, this 1 by r you can take equal to del square w by del x square, del square w by del x square. But so if you take large curvature, so this 1 by r you need not use, cannot write in this form, and it can be expanded. So, in that case, in case of this is not small, the curvature is not small, then you can use some other relation. So, that relation I will tell you. So, when you will derive the equation of motion for a large deflection beam just after this thing. So, by reducing, so you can reduce this equation by using these two fundamental equations and knowing the relation between the shear force and bending moment. So, you can derive this equation of motion of the Euler Bernoulli beam equation, which is nothing but your E I del fourth W by del x fourth plus rho A del square W by del t square. So, this will be equal to your f x t. Or in case of no external load or free vibration. So, this equation, so this right hand side will be equal to 0. So, it will be equal to E I del fourth W by del x fourth plus rho A del square W by del t square equal to 0. So, this part correspond to the inertia force of the system and this part correspond to the force due to the elasticity or the force due to the stiffness part of the system. So, this way you can derive this equation of motion. So, let us see this derivation again. So, in some books, so instead of writing F, so they are writing this shear force as V. So, this is shear force as V. So, for the small element F x t, so the total force can be written as F x t into dx, or so that means this F x t is the force per unit length and this is M is acting in left side, this is the bending moment, M plus dm is the moment in the right hand side. So, if you neglect the shear deformation, so that is this theta is very small, then you can write down this equation motion. So, first you just write down the force equation motion. So, that is V minus V plus dV plus f x t dx plus V equal to rho A x dx del square. So, this is the inertia force, inertia rho A. So, rho, so there I have taken rho as the mass per unit length. So, if you are taking rho as the density, so then this way also you can write rho into A, that is mass per unit length, into dx, that will give you the mass of that small element, into del square W by del t square. So, from this equation, so this V and V cancels. So, you got this dV, you can write dV always by del V by del x into dx and dm equal to del m by del x into dx. So, similarly, by taking the moment about the left side, so you can write down this equation. So, here they have taken this anticlockwise moment as positive. So, if you are taking this anticlockwise moment positive, then you can write m plus dm minus V plus dV. So, this is V plus dV into, so this distance equal to dx. So, you just see, so this V plus dV will produce a clockwise movement. So, that is why it is negative, and then this f x t dx, which will produce as it is taken in upward direction f x t dx. So, it will be into dx by 2. So, you can assume that it is acting, the total force is acting at the middle of the section. So, that is why you can multiply this dx by 2 and minus m. So, here the assumption is that this anticlockwise movement is positive. The previous case when I described, so I have taken the clockwise movement as positive. So, from this equation, so you can get this del m by del x minus V x t equal to 0. So, you can see this del m by del x equal to, so you cancel this thing. So, del m by del x minus V x t equal to 0, that is rate of change of your rate of change of angular, this rate of change of bending moment equal to the shear force, or this V x t equal to, so you know this V x t equal to del m by del x, V x t equal to del m by del x. So, from this thing, so you can find the equation motion, which we will see. So, from the second equation, so you can write this minus del square m x t by del x square plus f x t equal to rho A del square W by del t square. So, m after cancelling this m, so you got this thing, and by putting this m x t equal to E I del square W by del x square. So, you can write down this equation in this form, that is del square by del x square into EI del square W by del x square plus rho A del square W by del T square equal to f x t. So, here, so if we are taking some cross section, so for example, if the cross section is not uniform, so that time you can use this equation, that is del square W by del x square outside this thing. So, del square by del x square of EIX. So, if your sometimes this E also may be a function of x when you are using some functionally graded material. So, I may be a function of x also. I, for example, in this case I is, so in this case this cross section is not uniform. So, if the cross section is not uniform, so you can have different I. So, the I will vary along the length of the beam. So, if I is varying along the length of the beam, so you can take this del square by del x square outside and you can write down this equation, this del square by del x square into EIX into del square W by del x square plus rho AX del square W by del T square equal to f x t. So, if this external force is not there, then this f x t equal to 0 and this equation can be written as del square by del x square EIX del square W by del x square plus rho A into del square W by del T square equal to 0. Now, if we are taking this both E and I uniform, that is constant, then this EI can be taken out and it will reduce to the simpler form of this Euler-Bernoulli beam equation, that is equal to EI del fourth W by del x fourth plus rho A del square W by del T square equal to f x t. So, here in case of the free vibration, so this equation can be written. So, already we have written that equation, that is del fourth W by del x fourth plus rho A del square W by del T square, so equal to 0. So, this is for free vibration. So, this is for free vibration case and this is for the forced vibration case. So, you can see unlike the lumped parameter model, so this W is not a function of only time, but is a function of both time and, so it is a function of both time and this x, that is the position. So, it is a function of both time and position. So, let us see another example. So, in this case a simple slender beam is also taken. So, which is moving in vertical direction, that is ZT, it is moving in vertical direction with ZT. So, that is, for example, let me write this Z equal to Z0 cos omega t. So, where Z0 is the amplitude of the motion and omega is the frequency of that motion. So, that is, we have taken a base excited beam. So, let us use this Newton's second law or this moment based force and moment based approach to derive the nonlinear equation of motion of the system. So, in this case, so let us take a small element at a distance zeta. So, along the length of the beam, so we have taken the parameter as S is the parameter along the length of the beam. So, this is the x axis and this is the y axis. So, here in this beam, so let us, so a mass m is attached at an arbitrary position and so our objective is to derive the equation of motion for this beam. So, in this case as it vibrate, so let us take this v zeta t is the displacement along the transverse direction and u zeta t is the displacement along the axial direction. So, here considering inextensibility condition, so we can see there is relation between this u and v and we can reduce the 2 degrees of freedom motion, that is u and v, to that of a single degree of freedom motion, that is along u direction or along v direction. So, what are the forces acting? So, as we are considering this as an slender beam, so let us take this rho mass per unit length. Let rho is the mass per unit length of the beam. So, as we have taken at a distance zeta a small element d zeta. So, the length of this or the mass of this element will be rho into d zeta, and acceleration of this element. So, in two directions we can take the acceleration. So, in u direction, that is along these axial directions. So, let it is acceleration will be u double dot, and in this transverse direction this acceleration will be v double dot. So, the inertia force. So, if I am writing in terms of D'Alembert principle, so then we can find this inertia force. So, the inertia force will be, so for the small element the inertia force will act along this direction and along this direction. So, in this direction it will be equal to, so if we are taking this small element, so in this direction it will be rho, so d zeta. So, this is the mass of the element, so into acceleration. So, acceleration equal to, so acceleration will be equal to u double dot, and along this direction, so it will be equal to, similarly it will be rho d zeta into v double dot. So, these are the acceleration or this inertia force acting in this element. Similarly, for the attached mass, so if the mass is m, so we can write this inertia force in the similar way. So, it will be equal to m v. So, at that position, for example, so let it is at a distance d. So, we can use this Dirac delta function to write this position of these things. So, we can write using this Dirac delta function zeta minus d zeta minus d. So, it will be, the force can be written m u m delta zeta minus d v double dot, and another force it will be equal to, or this is the inertia force zeta minus d into u double dot. So, this is in this longitudinal direction and this is along the transverse direction, the inertia force is acting. So, like this Euler-Bernoulli beam equation, so we can write this moment m. So, moment m can be written equal to EI into this EI into phi dash, or EI into, or you can write this EI into k, ks, that is radius, that is curvature, ks will be the curvature. So, generally we can write this is equal to ks, and this ks can be written as phi dash. So, you can see, so if we are taking this angle equal to phi, so this phi, so this is v. So, at a distance, so we can draw this small. So, for example, so this is the x direction. So, displacement equal to, so along the beam we have taken, so along the beam we have taken a distance ds. So, this is dx along the x direction, and this is our dv, small displacement along the transverse direction. So, this angle equal to phi. So, one can easily write this sin phi. So, sin phi will be equal to dv by ds. So, as sin phi equal to dv by ds or v dash. So, we can differentiate this and we can write, so this is cos phi into d phi by ds, cos phi into d phi by ds equal to, so this is equal to v double dash, or d by ds of v dash. So, that is nothing but v double dash. So, we got this cos phi into d phi by ds equal to v double dash, or phi dash equal to, so phi dash you can write this, now you can write this phi dash. So, we can write, so So, now this phi dash can, so already you have written this sin phi equal to dV by ds or cos phi d phi by ds. If you differentiate this thing equal to V double dash. So, now this d phi by ds can be written. So, d phi by ds equal to V double dash by cos phi, but this cos phi can be written as, so this is V double dash by cos phi can be written as 1 minus sin square phi root over. So, this is nothing but V double dash by, so already we have taken this sin phi equal to V dash. So, it is equal to root over 1 minus V dash square. So, we can write this equal to 1 minus V dash square to the power minus half into V double dash. So, this is equal to, so by expanding this thing binomially, we can write this equation equal to half V dash square into V double dash. So, you can see this d phi by ds can be written as V double dash into 1 plus half V dash square. So, previously you have seen this m, that is moment equal to EI Ks. So, that is nothing but your EI phi dash. So, this is further can be written EI V double dash plus EI V double dash into, so this is half into V dash square. So, when you have not considered this phi to be small, in that case, so we have this additional term, that is half EI V double dash into V dash square. So, this introduces the nonlinearity in the system. Otherwise, in case of Euler-Bernoulli beam equation, so you have seen only this term due to this bending, that is m equal to EI del square V by del S square, but now we are considering an additional term, that is half EI V double dash into V dash square. So, if we can, you can see now this derivation. So, quickly we can visit this derivation. So, already I have written this derivation. So, you can write this ms equal to EI Ks and k equal to del phi by del s equal to phi dash, and taking this sin phi. So, this angle we have taken as phi. So, sin phi already I have explained that sin phi equal to V dash. So, phi dash equal to V double dash by root over 1 minus V dash square, and by taking that thing to numerator and expanding using binomial theorem. So, we can write, so this is equal to EI V double dash into 1 plus half V dash square. So, this taking the moment, so taking the moment about this S. So, at a distance S, let us find what is the moment. So, and taking a dummy variable d eta. So, now we know what are the forces acting, already I explained the forces acting in the system. So, let us take the forces, inertia forces along the transverse direction as m1, moment due to inertia force along transverse direction as m1, moment of the forces along longitudinal direction is equal to m2, and the moment due to the rotary inertia equal to m3. So, we have these three terms. So, we can write, so this way we can write. So, m1 will be this. So, already we know the force equal to rho v double dot minus rho v double dot. Also for the mass, this for this attached mass m. So, it is m using this Dirac delta function, it can be written. So, m delta zeta minus d v double dot, that means when zeta equal to d. So, this term will equal to 1, otherwise this is equal to 0. So, this integration m delta zeta minus d v double dot equal to 0 when zeta not equal to d. When zeta equal to d only it will have a value, otherwise it is equal to 0. So, if we include damping also. So, by putting this damping C V dot, so we can write this m1. So, damping, for example, C, let us take coefficient of damping in this transverse direction as C. So, then this moment will be equal to, say, if we are taking moment. So, this is the moment. So, this moment will takes place along V direction. So, then the perpendicular distance. So, we have taken a small, let this is the dummy variable zeta. So, the perpendicular distance will be along this. So, it will be the cos component of that thing. So, that is why this cos component is multiplied. So, it is cos phi into d eta. So, this integration is taking place from s to zeta. So, this is the moment equation for taking the force in the transverse direction. Similarly, taking the force along the longitudinal direction, that is u direction. So, you can write this equation of motion. So, rho u double dot, then minus rho g is the weight component, then m delta into zeta minus d into u double dot minus g, as g is acting vertically downward. So, this is u double dot into g, and the distance, multiplication of the distance is nothing but sin phi d zeta, sin phi d eta into d zeta. Similarly, taking the rotary inertia, let J the rotary inertia of the system. So, due to this mass, the rotary inertia of the system, then this will be multiplied by rotary inertia into phi double dot, that will give you the m3 integration of s to L j delta zeta minus d phi double dot d zeta. So, this is the rotary inertia due to this attached mass at an arbitrary position. So, this part of the derivation actually published in this Journal of International Journal of Nonlinear Mechanics, volume 34 in 1999. So, by Professor R.C. Kaur and myself. So, this is part of my PhD work actually. So, you can see this derivation. So, now you can see, so by writing this m equal to, so you can write ms equal to ei. Now, already we got this is equal to ks equal to this m1 plus m2 plus m3, and now m3, and differentiating it twice. So, one can get this equation. So, this equation becomes ei del fourth b by del x fourth plus half del fourth w by del s fourth into del v by del square plus 3 into, so let us write in terms of v dash. So, 3 into v dash into v double dash into v triple dash plus v double dash cube plus 1 minus half v dash square into rho plus m delta s minus d into v double dot plus cv dot plus v dash into v double dash integration s to L rho plus m delta zeta minus d v double dot plus cv dot d zeta minus d del by del s into j delta s minus d v dash tt means differentiation with respect to twice differentiation with respect to time minus del by del s into n into v dash equal to 0, where this n term is written here. So, you just see, you can note here that only for the Euler-Bernoulli beam. So, we have the first term, that is ei del fourth w by del s fourth, and one more term that is there, that is rho. So, one more term we have. So, this is the term rho v double dot equal to 0. So, other terms are coming. So, for example, this term is coming due to the additional mass in the system, and also, so there are several nonlinear terms present in the system. So, you can see all these terms are nonlinear terms. So, by taking this large amplitude oscillation, so we have seen, so the equation of motion contain many nonlinear terms. So, here you can note that this v s t is a function of position s, and time t. So, you can convert this thing to its temporal form by using this Galerkin procedure. So, where you can use this Vst equal to summation. So, you can take several modes into account. So, psi I s into q I t. So, this is variable separation methods you can use. So, where you can take let us take single mode approximation. So, if you take single mode approximation, so this work reduces to that of Javodini and Nafe. Javodini and Nafe paper of 1989. So, published in the Journal of Nonlinear Mechanics related to this vibration of a similar system. So, but if you take 2 mode into account, so it will reduce to my own paper in this same journal, and you can take 3 modes also. So, I have several works related to 3 modes also. So, you can take I equal to 1 to infinity, or you can take I only single mode, 2 modes or 3 modes depending on different type of applications. So, then you can reduce this thing by applying this Galerkin method. So, by substituting this in this equation and using some weight function, you can find the residue and equate the residue equal to 0 to find the equation of motion. So, you can find the equation of motion in this way. For example, by substituting this, so you can write down this equation of motion in this form un double dot plus, so here you just see un is a function of time only. So, un double dot plus 2 epsilon zeta n un dot plus omega n square un minus epsilon m equal to 1 to infinity fnm cos phi tau plus epsilon k equal to 1 to infinity, L equal to 1 to infinity, m equal to 1 to infinity, alpha n klm uk ul um plus beta n klm uk ul dot plus gamma n klm uk ul double dot. So, you can see this term, that is uk ul So, if k l m are equal to 1, then it reduces to u cube only. Similarly, so here it will reduces to u1 into u1 dot square. So, product of two velocity term is a acceleration term. Similarly, here it is u m double dot. If it is single mode, then it is u1 double dot. So, u1 double dot is nothing but this acceleration. So, this is also an acceleration term and this also an acceleration term. So, that is why these two terms are known as inertia nonlinear term, inertia nonlinear term, and this is geometric nonlinear term. So, if you neglect this acceleration, then these two inertia terms will be 0. If the acceleration is very small, then these two terms can be neglected and the only term will be the geometric nonlinear term, and this equation can be reduced to that of a equation which you have seen before. So, this inertia, so let me tell this forcing term, then I will tell the equation. So, in this case you can see in the forcing term, this coefficient of um is a time varying term. So, that is why this equation is known as the equation of a parametrically excited system. So, this is the equation of a parametrically excited system with nonlinear term. So, you have seen the equation of a parametrically excited term as Matthew equation and Hill's equation in the introductory class. So, in this case, so you have this additional nonlinear term, additional geometric and inertial nonlinear term in addition to that Matthew type of equation. So, we can see, so in this way you can derive this equation of motion of any single any continuous system. So, by taking a small element, you can write down this moment equation and by writing this moment equation. So, you can derive this equation of motion. Similarly, this work you can this as an assignment. So, you can derive this equation of motion of a base excited cantilever beam with a tip mass attached to this thing and subjected to a follower force. So, let a force Pt is also acting in this beam. So, in this case, so you can derive this equation of motion. So, previously in the inextensibility conditions was taken. So, this displacement in x direction is written as a function of the displacement in y direction by using this relation, that is V s square plus 1 plus u s square equal to 1, where V s equal to del V by del s and u s equal to del U by del s. So, using this relation, so this is the relation for the inextensibility condition. So, the previous equation was derived. Here also you can derive this equation of motion by using similar approach. So, you can have many different applications or many different this type of continuous systems. For example, you may put one piezoelectric patch also here. So, for sensing and actuation purpose. Also you can take this as a magnetic material and apply the magnetic field. So, you can apply the magnetic field B also in the system. So, there can be several applications of this type of system, for example, micromechanical, electromechanical systems or smart systems. So, these derivations will be very much useful in different applications. So, you should know how to derive this nonlinear equation of motion. So, briefly just I will tell you how to use now this Lagrange principle. So, initially we have done this force and moment based approach, where we have used this Newton's second law or D'Alembert principle. So, then in this energy based approach, so we are going to use this Lagrange principle, where we can write this Lagrange principle as d by dt of del t by del q k dot minus del t by del q k equal to capital Q k, or using this Lagrangian of the system, that is L equal to T minus U, where U is the potential energy, T is the kinetic energy. The same equation can be written as d by dt of del L by del Q k dot minus del L by del Q k equal to capital Q k. So, here this Q k is known as the generalized coordinate. So, this is generalized coordinate. So, this generalized coordinate, what do you mean by generalized coordinate? For example, so already I told for a given systems, so we have both physical coordinates and generalized coordinate. So, for example, in this case of the simple pendulum, so you can write down this equation using the coordinate x and y, that is the physical coordinate. Okay. So, physical coordinate, but you can see that this x and y, they are depends on each other. For example, they are related by this constraint equation, that is x square plus y square equal to L square. So, if this point we have taken 0 0 coordinate, this is x y, then the length of the simple pendulum is constant. So, that is x square plus y square equal to L square. So, by using this you can write either x in terms of y or y in terms of x, but conveniently you can use another parameter, that is theta, for writing the equation of motion. So, here theta is the generalized coordinate, and using this generalized coordinate theta, so you can write this kinetic energy and the potential energy of the system, and you can find the Lagrangian of the system. Then you can write this d by dt of del L by del q k dot. So, here q k equal to 1. So, this q equal to theta in this case. So, q equal to theta, you can find this equation of motion. Similarly, this capital Q k is known as the generalized force. So, this generalized force equal to let. So, in the system a number of forces are acting, F1, F2, F3. So, from some position, so this is the position physical coordinates you have taken. So, let this force is at a distance, position vector of this force is at r1, r2, r3, r4. So, then this qk can be written as I equal to summation I equal to fi dot del ri by del qk plus I summation I mi dot del omega I by del qk. So, this is equal to generalized force. So, if moment is not there, moment is not working, then it will be only this force qk will be equal to summation fi dot del ri by del qk. So, tomorrow class we will solve, or next class we are going to solve some problems on this using this Lagrange principle. Also we will study the extended Hamilton principle to derive this equation of motion. So, we will see both linear and nonlinear equations, and we will complete the derivation of equation of motion, and this will complete the module, second module in the next class. So, thank you very much.